So we'll finish up our look at atomic physics with an examination of two phenomenon that are the results of atomic emission. The first phenomenon that we'll discuss is the production of X-rays. X-rays were discovered more or less by accident by William Röntgen in 1895. He had a cathode ray tube and he discovered that some rays got produced that caused a screen in his lab to fluoresce or to glow. Now, the way that they're produced is you have a regular cathode ray tube. We already talked about cathode rays. We now know are electrons. And the electrons hit a metal target, and when they do that, they cause X-rays to be emitted. Now, here's the way this works. You have to get your incoming electrons to be very, very energetic because they have to overcome the repulsion of the other electrons in an atom. But if those electrons are energetic enough that they can actually reach the inner electrons of an atom, they can knock it out. And then you have a gap in the lower energy levels of your atom, and so one of the electrons from one of the upper levels can fall down to that lower level, but that's a huge energy gap right there, and so the photon that gets emitted has a lot of energy, and in certain cases it will be an X-ray photon. So let's see if you can apply some of the logic that we used when we learned about the photoelectric effect to what is in some ways kind of the reverse situation. Here in the production of X-rays, we have electrons striking a metal target and they are causing photons to be released. Now, in order to get those electrons to be able to release the photons, the electrons have to have a lot of energy. So you need a big accelerating voltage in order to get the electrons up with enough energy so that they cause an X-ray to be released. So imagine then, if you have this happening in a particular X-ray tube, the maximum frequency that you have of emitted X-rays is F0. Now, if you double the accelerating voltage, what will happen to the maximum frequency of the X-rays? Go ahead and think about it, stop the video, and when you have an answer, you can start it back up again. The answer is that the frequency, the maximum frequency is going to be the same. The accelerating voltage just makes the electrons more energetic. But remember, all the energetic electrons do is they knock off an electron from one of the inner shells of the target atom. The frequency of the emitted X-ray is determined entirely by the energy difference between one of the outer energy levels of that atom and the inner energy level which has lost an electron. So that's not going to change. You might get an increased production of X-rays because now you have more electrons that have enough energy to knock off one of those inner electrons from the target, but you're not going to change the frequency of the emitted X-rays. The second phenomenon involving atomic emission that we're going to study is the laser. Now, laser is actually an acronym. It stands for Light Amplification by Stimulated Emission of Radiation. Basically, what's going on here is this. If you have an atom with some energy levels, and you have some of your electrons in their energy levels have been excited, and so they are in higher energy levels, if you shine photons in of just the right frequency, the frequency that would match the frequency of a photon that would be emitted if the electron were to drop down to a lower level. So if you take photons of just that right frequency and pass them by those electrons, the electron can be stimulated to be emitted and stimulated to fall down to lower level, I should say, and when it falls down to lower level, it emits a photon of the exact same frequency as the incoming photon. Remember, when you have spontaneous emission of photons, you can't predict exactly when it's going to happen. You can only say what its probability is. but you can increase that probability greatly by having photons of just the right energy coming in, and they will stimulate the emission of more photons of the same frequency. So let's compare spontaneous and stimulated emission of radiation. Well, spontaneous emission, because it happens at random times, you can't cause it to happen, it's a much less intense light. And it also occurs in random directions, so all the light is not going in the same direction. And the photons are not in phase with each other. In phase, it's easiest to think of it if we go back to our wave model for light. When two waves were in phase, their peaks overlapped peaks and troughs overlapped troughs. Whereas with laser emission, with stimulated emission, a spontaneous photon can cause others to be emitted, and of course that has a cascading effect when other photons get emitted from the stimulated photons. And the nice thing about it is that it occurs in the same direction as the incoming photon. This leads to a very intense light beam because all the photons are going in the same direction. And they're in phase with each other.